Hello again, everyone. Imagine a shiny metal spoon in your hand. You know there are billions of electrons dancing inside it, so why don't they simply fly away? Inside a metal, these free electrons move like swimmers in a pool, bumping into atoms but never leaving the edge. The moment an electron tries to escape, the surface becomes positively charged and tugs it back, like a magnet pulling a pin. This creates an invisible energy wall called a potential barrier. Only electrons with enough energy can climb over it, just as a ball needs a good push to roll over a hill. So, the challenge is clear: how can we give electrons enough energy to break free? To measure that challenge, we define a beautiful quantity, the work function, written as phi naught. It's the minimum energy an electron must gain to leave the metal's surface. Each metal has its own phi naught depending on its atomic bonding and surface finish. We measure it in electron volts, the energy an electron gets when accelerated through 1 volt. 1 electron volt equals 1.602 times 10 to the power minus 19 joules. For example, sodium, with phi naught of 2.3 electron volts, lets electrons escape more easily than platinum, whose phi naught is 5.6 electron volts. So, metals differ in how tightly they hold onto their electrons. Some cling, some let go. Now, let's see how we can actually help electrons cross that barrier. Nature gives us 4 clever ways. First, thermionic emission. Heat the metal so that atoms vibrate wildly, jostling electrons free. Second, field emission. Apply an intense electric field, nearly 10 to the power 8 volts per meter, which literally pulls electrons out. Third, photoelectric emission. Shine light of the right frequency, and photons hand over their energy to the electrons. And fourth, secondary emission. Let high-speed electrons strike a surface, knocking others out, rather like billiard balls colliding. Different energy sources, heat, electricity, or light, all achieve the same goal, giving electrons their ticket to freedom. Let's warm things up, literally, with thermionic emission. When metals such as tungsten or barium oxide are heated red hot, their electrons gain enough thermal energy to jump the barrier. This principle powers cathode ray tubes and old vacuum tube radios. The emission current grows dramatically with temperature, and scientists describe it with the Richardson-Dushman equation, J equals A times T squared times exp of open bracket minus phi naught divided by KT close bracket. Here J is the current density, T is temperature, is work function, K is Boltzmann's constant, and A is the Richardson constant. So next time you see the orange filament of an old tube, remember, you're watching thermionic physics in action. Now let's explore two other thrilling routes, field and photoelectric emission. In field emission, a colossal electric field at a sharp metal tip bends the surface barrier so tightly that electrons can tunnel through it quantum style. This phenomenon runs devices like field emission microscopes and spark plugs. Meanwhile, photoelectric emission is all about light. When photons of sufficient frequency strike a metal, each photon transfers its energy h times f to an electron. If that exceeds the work function phi naught, the electron escapes as a photoelectron. This is the principle behind photoelectric cells, automatic doors, solar panels, even camera light meters. Let's crunch a quick example together. Suppose a metal has a work function of 2.5 electron volts. What's the minimum frequency of light required to eject electrons? We know energy equals h times f and must equal the work function. So F equals phi naught divided by h equals open bracket 2.5 times 1.602 times 10 to the power minus 19 close bracket divided by open bracket 6.626 times 10 to the power minus 34 close bracket. That gives F 6.05 times 10 to the power 14 Hz light in the violet ultraviolet region. So only light above that frequency can kick out electrons. The math beautifully matches our quantum picture. Each photon must deliver at least phi-naught energy to liberate an electron. Let's recap what we've discovered. Metals hold free electrons, but an energy wall, the work function, keeps them bound. Provide enough energy through heat, electric fields, or light, and they escape as emitted electrons. These processes power everyday technologies, thermionic walls in early electronics, photoelectric sensors in doors and solar cells, and even electron microscopes that image atoms. Electron emission is where classical physics meets quantum energy. It's the first step toward understanding the photoelectric effect and the true dual nature of light and matter. I hope you enjoyed exploring how we can literally coax electrons out of metals. In our next session, we'll dive into the photoelectric effect itself, where light turns into electricity in the most astonishing way. See you there.